Ah. Okay, good morning, students. You can, if you have any questions at any point of time, please feel free to stop me. The chat, this thing is also enabled. So if you have any questions, you can post it there. So am I audible first of all? Can you hear me?
Yes, sir.
Okay, so I think we can start. Unit 5 is the last unit of our syllabus, and I'll try to go a little fast so that we can finish the full unit today. And I might not touch all the topics because some of them are simple. So I'll just go through the important topics first, and then based on how much time we have, maybe we can complete the other topics also. So the first, this thing I'll jump quickly. I'll not do this in detail, but this approach is basically called as the method of bubble pushing. And just like the name says, the bubble is for the inverter. And the idea is this first figure that you see here, figure A. Okay, it's implementing some function which is AB plus CD, and it is implementing in terms of AND gates and OR gates. And by now, all of you know that CMOS is naturally inverting, which means that AND and OR cannot be implemented directly. So what we want in the implementations, that is in the gate level circuit also, sorry, gate level diagram also, we don't want AND and OR. So that is what this method tries to do. Anytime you have a AND gate, okay, what you do is you add two inverters at the output. So that is what is happening in diagram B here. AB AND gate, which is there in A. We are not changing the functionality because we're adding two inverters. But then what we can do is we can pull one inverter back to the AND gate itself and make it a NAND gate. And the other inverter, we push it to the next stage. That is why it is called as pushing. And to the next stage allows you to possibly, okay, that's not a guarantee either. In some cases we can do it, in some cases we cannot do it. And this example, clearly we can do it because when we push the inverter to the next stage, we have this inverted inputs coming to the OR gate, which in terms of our De Morgan's law is nothing but a NAND gate. So that is what is the idea behind this method of bubble pushing. You just add wherever you have AND gate or OR gate, okay, add two inverters, and one you add to the AND or OR gate itself to make it NAND NOR, and you continue with the other one and you try to convert that into some other NAND NOR gate. And this is the simple idea behind this method of bubble pushing. And you can try some examples also. For example, one question is here: create a 6-input OR gate using only NAND NOR gates. So the only thing to remember is it's not possible to do this all the time. Okay, it might fail sometimes. So it is possible in some cases. But one thing to remember, I mentioned this in my class, I mentioned the same thing again. Whenever we are dividing it, okay, so for example, I'll take this example itself, 6-input OR gate. I'll switch to the whiteboard one second. Okay, so suppose I have a 6-input OR gate, which is the question I have now. Okay, and I want to convert it into in terms of NAND NOR. So we can do that. It's very simple. 4, 5, 6. So it's a 6-input OR gate. Okay, and generally we can convert that into 2-input gates or 3-input gates. So one possibility is 1, 2, 3, one OR gate, and 1, 2, 3, another OR gate, and both of them you give to another OR gate. Okay, and now add the inverters here and here, here and here. So this becomes a 3-input NOR gate, which is very good for us. And bottom also is a 3-input NOR gate. And this output here, okay, this gate, we can replace it with the NAND gate. How can we do that? We can do that because what is happening here, I'm getting inverted inputs. So the inputs to the gate are A bar and the other input is B bar, and this is the OR gate. So A bar plus B bar is the output, right? So A bar plus B bar, we also know from De Morgan's law is AB the whole bar equal to A bar plus B bar. So this is a NAND gate and this is a OR gate with inverted outputs. So basically both are equivalent. That is how we can replace this with this. Okay, but one thing to remember is this works well only if you have an even number of stages, because clearly if you have an odd number of stages, in the third stage, how can you convert it, right? You will be stuck with one gate. So for example, here, if you convert it somehow into 3 stages. So for example, you do this. Okay, so in this case, you will be stuck. So I'll just clear the screen and do it again. Suppose you convert it in a different way, which is not wrong, but you will not be able to do this bubble pushing exactly. So if you do it like this, and then here you combine it. So basically 3 stages of logic if you use, okay, you will be able to do the bubble pushing here. But this gate will be stuck because there's nowhere to push. Okay, so that is going to create a problem for you. So as far as possible, in any of the examples or the numericals they ask, try to divide it into a even number of stages, 2, 4, like that. Okay, so this is in brief the method of bubble pushing, just a technique to improve the gate delay. So the next another family of gates, and we have already seen some of these examples, it's not new, but another very important family of gates is the AOI and OAI, because many times in our logic expressions it's in sum of product of some form, and those can be represented using this and or invert, which is SOP, and or and invert, which is product of some form. And this is also available as part of the standard cell library. If you look at the standard cell library, or if you look at the synthesis report, the cells that have been used, many times you will see this AOI and OAI cells because they occur very commonly. They are part of the standard cell library. So for these gates also, we can calculate our usual metric, which is the logical effort. And we have done this for the NAND gate, NOR gate, etc. Same way we do it for this also. Okay, we just have to find the equivalent inverter, and then for each input, the input capacitance divided by input capacitance of equivalent inverter. But the only thing is, in this particular family, if you see this gate here, okay, this is AB plus C, the whole bar. This is called as AOI 21, because one side you have 2 inputs, A and B, and the other side we have only 1 input, C. Okay, so in this particular case, I implement the gate and I size it similar to equivalent inverter. I get all these numbers which you see on the right hand side. But one thing that is different is the logical effort is yeah.
The screen is not visible. Screen is not visible.
Sorry, can you see it now?
Yes, sir.
Okay, thanks. So sorry about that. And or invert, like I was saying, is a compound gate. It's called as a compound gate. But the only difference, okay, other than that, everything is the same. The way you draw the circuit, the way you give the sizes, etc. There is a possibility that the logical efforts are not the same for all the inputs. And you can see that in this example, there are 3 inputs, A, B, and C. A is connected to 1 NMOS and 1 PMOS. The total input capacitance is 4 plus 2, 6. And the equivalent inverter is input capacitance is 3. So logical effort of A is 6 by 3. Same for B, 4 and 2. So that is also 6 by 3. But C is connected to total input capacitance of 4 plus 1 equal to 5, not 6. Okay. So in these cases, we will have to write the logical effort of each input, GA, GB, and GC. They're not the same. And this is not the case all the time. In this particular case, you see that it it is equivalent because this thing is symmetric, AB plus CD. This is called AND or invert 2-2 because there are two inputs AB and two inputs CD, and the gate with the sizing is shown, and all the input capacitances are the same, 4 plus 2 6, so it is 6/3 for all the inputs. Oh, one more example is that you can try this on your own. It's also solved in the book. Okay, so next topic, input ordering effect, and a lot of definitions are there, but we will just see it with a example. Okay, so let us just take one example. We'll switch to the whiteboard. So what is the meaning of this input ordering? So first of all, we have to remember that in practical circuits, so I've done all this in cadence, and we only give the inputs, right? V pulse, V use, and many times the inputs are basically coming at the same time, meaning that you give the V pulse period, something is 5 nanoseconds, 10 nanoseconds, and the inputs are rising at the same time. But in practical circuits, it's very rare that all these inputs will come at the same time. So for example, if you see a typical waveform, okay, it might be that this is one input A, and this is another input B, okay, and then there might be a third input C. So this is what will happen in the practical situation. The A, B, and C, they will never come at the same time. In this case, for example, C comes first, then A arrives second, and the last to arrive is C. And this order will be the same. Why this order will be the same? Because the signal A, okay, is generated by some block, some logic block, which is supplying it to your design. Signal B is generated by some other logic block. Okay, and signal C also same thing. It is generated by some other logic block. And I've drawn the logic block with different sizes to show that the delay of C is minimum. Okay, it's a very small cell. So quickly the output is coming. Delay of A is not so small, but it's still okay. It's coming second. B is a very large logic block and it produces the output last. And this order will not change. Okay, the order in which the signals arrive to your gate will be the same. So in that particular case, the question that we are asking is, how can we optimize the design? So there's a question. Did you mean to raise your hand or it happened by mistake? 19CS002. Someone from computer sciences in this meeting? Okay, so what are we trying to do? We have a gate. So let's draw a simple 2-input gate to begin with. Okay, so any gate is fine. Let's say we choose a 2-input NOR gate or 2-input NAND gate rather. What is the idea behind this input ordering? It's a very simple idea. Okay, so if you look at this 2-input gate for the pull down network, okay, there are a total of 2 capacitances. One is the load capacitance, or what we call as CL, which is the sum of the diffusion capacitances connected to the output and maybe some other gate capacitance. And one more is this intermediate capacitance. Okay, so suppose we want to discharge the output, that is the output has to go from 1 to 0. Okay, that will happen through the pull down network, right? So when we are trying to discharge this, okay, what will be better for us is if this was already discharged. That is the whole idea of this input ordering. Suppose we have 2 signals, okay, and this signal, okay, suppose we have 2 signals, and just like I mentioned, they might not come at the same time. Suppose this signal, let's call this A and B. Okay, so let's say that A comes first. First is A, and second is B. Okay, so A has already come, which means that A has gone from 0 to 1, and this MOS is conducting. Okay, but B has not yet arrived, which means that this is a open circuit. which means this capacitor cannot discharge. Even though A has come, the signal has come, but we are not doing anything, right? So that is the bad thing. So how can we improve that situation? It's very simple. We can improve that situation by changing this order. That is what is the meaning of this input ordering. Suppose I change this order, right? What I mean is, instead of A and B like this order is fixed. First A comes, okay. Second B comes. So what I'll do now is, when A has arrived, that is A has gone from 0 to 1, okay, this capacitance will get discharged. So I can completely remove this capacitance. It's out of the picture, okay. So A has come, the intermediate capacitance is discharged. So now after some more time B will come, only the output capacitance has to get discharged, and that is the simple idea behind this input ordering effect. Okay, you order the inputs because we can decide which is A and B, right? We know from our experience that changing A and B doesn't change the function. It is still a 2-input NAND gate. It is still giving me AB the whole bar. I'm not changing that, but by giving the signals correctly, that is the ones that come first, the signals that come first, they should discharge the intermediate capacitances, and when the final signal arrives, only the output capacitance has to be discharged, which means that will happen very fast. Okay, in the previous case, first the signal came, but now capacitance was discharged. So when the final signal came, both the output capacitance and the intermediate capacitance have to be discharged, which means it's going to take more time. Okay, so that is the idea behind this input ordering delay effect. So I'll just quickly copy and paste this question and we'll try to solve it. Okay, so this is the question. The 3-input NOR gate. Okay, so let us first draw that gate. 3-input NOR gate. So there's a lot of definitions. They are basically saying the same thing only. You can read them also, but the idea is very simple. You don't need to know any of the definitions. Just use the logic that we have just discussed. Okay, there are many intermediate capacitances, and we want the signals to be such that as they come, they are able to discharge some of the intermediate capacitances. So in the bottom part, the order doesn't matter. Okay, because there is only one this thing in the load capacitance, and anytime a signal comes, that will get discharged. So in this case, we have to be concerned about the pull up network. So pull up network, okay, we have to charge these capacitances and also the output capacitance. In this case, we are concerned about the capacitances going from 0 to 1, all of them, 0 to 1, 0 to 1. Okay, so in this case, again, the idea is when the final output comes, only the load capacitance, only this capacitance has to be charged. Okay, this capacitance should be charged, this capacitance should already have been charged. So that is the simple idea. So how can we do that? So there are 3 transistors in series. So suppose you have the first signal. In this case, we are saying is first signal is C. Suppose I give C here. Okay, so if I give C here, now these 2 transistors are not conducting, so there will be no path to VDD. So that will be a mistake. I should not do that. Okay, so then you try the other one. Suppose you give C here. okay, it will still not be able to charge this capacitance because this transistor is not conducting. So that is also not correct. Okay, so the correct answer is give C to this transistor. So as soon as C comes, this is the first signal to come. This will be conducting and it will be able to charge this particular capacitor, and the first intermediate capacitances has reached the final value. Now this transistor is conducting because C has arrived. Next signal to arrive is A, to give A here. So once this is come, C is already conducting. Now the second capacitor also it will be able to charge. And finally the third and last signal is B. And when B comes, only the output capacitance needs to go from 0 to 1. This is already at 1. This capacitor is already at 1. So this is the idea behind this input ordering effect. You can give the inputs in such a way that all the intermediate capacitances are charged, okay, and when the last signal arrives, only the output capacitance needs to be charged. So that is the idea behind this input ordering effect. Okay, so let's go back to the slides. Okay, so the next topic is called as this skewed gates. So what is the meaning of skewed? Skewed is just an English word meaning sort of tilted. Okay, you might have heard of this clock skew. It means that it is somewhat not the perfect middle. Okay, it's tilted to one side or the other. Clock skew means it's not arriving at the exact time. It's either arriving before the time or after the time, positive skew or negative skew. Same thing here also. Skewed means it's not having the exact sizes that we want. Okay, what is the meaning of exact sizes? We have sized the gates so that the pull up network and pull down network have the same equivalent resistance. That is what is the idea we have used for all the gates that we have designed, including the compound gates, including the Nand gate, NOR gate, etc. For all the gates, the rule that we followed to get the 2:1 for inverter, then 4:4:4:4 for NAND gate, etc., is that the NMOS and PMOS networks, not the individual transistors, the networks should have the same resistance, which means that the output rise time and fall time, okay, that is the TPHL, TPLH, sorry, not rise time, fall time, TPHL, TPLH will be the same. Now, there might be some cases when this is not necessary, okay, and those cases typically are when one particular transition is very important. So, for example, emergency signal, okay, in this thing in digital circuits, for example, a reset signal. Suppose something is going bad. Suppose the system is getting too hot, okay, and a reset signal might be generated based on the temperature sensor value, or a switch off signal might be generated based on the temperature sensor value. So switch off signal is generated means very quickly you should respond to that, right? But once the signal goes from 1 to 0, 0 to 1, okay, 0 to 1 transition should happen very quickly because it's a very important signal. But 1 to 0 is not so important because there will be many other things that are happening in parallel at that time. So in those particular cases, okay, we can try to optimize the performance. That is, the 0 to 1 transition should be very fast. 1 to 0 transition not so fast. Okay, that is the idea behind this skewed gates. And the sizing rule is very simple. Okay, what is the sizing rule we are going to use in these cases? The whichever is the critical transition, okay, that is the critical transition means it can be either 0 to 1 or 1 to 0. 0 to 1 is the critical transition means it happens through the pull up network. 1 to 0 is the critical transition means obviously it happens through the pull down network. Okay, so how do we do this sizing in this skewed gates? Okay, this thing is very simple. It says here, okay, for critical transition, leave that particular network untouched, meaning that don't change any of the sizes. whatever you were putting before, you put the same sizes. Don't change that at all. Okay. The other network is there, right? Which is the other network, the pull down network. If the pull up network is critical, or the other way around, you make it half the required size. Okay. So this will be very simple if we do it with some examples. So let us do it for the three cases: inverter, NAND gate, NOR gate. Okay, so we'll start with each this thing. So we will look at both high skew and low skew versions for each of those gates. And then we will look at the logical effort also, because that also has to be calculated. So let us start with the inverter. Okay. So let us draw the usual inverter, and then we will do the high skew and the low skew versions. So I'll put the sizes 1, 1. This is obviously not the regular inverter. This is a skewed inverter. Can you guess if this is a high skew or a low skew inverter based on the rule that we said? What we said is whichever is the critical transition, you leave that transistor size untouched. Okay. The non-critical transition, you make that half the normal size. That is what I have done here. Okay. This should have originally been 2, but I have made it 1, and this should have been 1. I have kept it at 1, which means that this is the critical transition. That is the 1 to 0 is very important for this particular gate, which means that it is a low skew inverter. Okay. This is the meaning of the low skew inverter. Whichever transition is critical, in this case 1 to 0, high to low transition, you keep that transistor at the same size, that is 1. Okay. This transition is not so important. Maybe it occurs very rarely, or it's not very important to make the transistor, the output go from 0 to 1 quickly. So you make that half. Now, next question is, what is the logical effort of this particular gate? Okay. And for that, we cannot just say the logical effort is 2 by 3. Okay. The reason for that is, what is the meaning of logical effort? Logical effort is with respect to equivalent inverter, right? Inverter, equivalent inverter will be the same 1 by 1. But in this case, the transitions, we have to size the equivalent inverter for each of the transitions. What is the meaning of that? GU and GD will come into the picture. That is pull up and pull down. Why that will come into the picture is each of these transistors are not equivalent. Okay. So what I am saying is, I'll just do the thing. When I'm doing the logical effort for pull down, that is GD, this one, okay, I will put it identical here. But I cannot put the same thing here, okay, which means it is the same inverter. For a inverter, if the NMOS is 1, for a normal inverter, PMOS will be 2. Therefore, GD equal to input capacitance of my gate, which is 1 plus 1, 2, divided by input capacitance of equivalent inverter. For that transition, we have to add, okay, for these particular skewed gates, because the transistors are not of equal strength, the transitions have to have different equivalent inverters. So in this case, the equivalent inverter is 1 and 2, and the logical effort is 2 by 3. And the same thing if you do on top, this time what you should do is PMOS size you should put as the same. Okay, that is, if the PMOS size in your gate is 1, here also we put 1. How much we put for the NMOS? For that, don't look at this gate again. For a normal CMOS inverter, if this is 1, this is 1 by 2. So therefore, GD equal to 1 plus 1 is 2 divided by 1 plus 1 by 2 is 3 by 2, which is equal to 4 by 3. Okay, so this is the logical effort for the rising transition, and clearly excuse me, clearly the logical effort for the rising transition is higher than a normal inverter. Normal inverter is 1, but in this case it is 4 by 3. But that is acceptable for us because this is not the critical transition. But the critical transition, this has become better than a normal inverter. Normal inverter is 1, this is 2 by 3. Excuse me. Okay, so let us do one more gate. Let us try it for a NAND gate. So this time let us do a high skew, okay, which means that whatever sizes we put for the original NAND gate, those have to be the same, that is 2 and 2. Okay, here we would have put again 2 and 2, but this is a high skew. We don't care about the high to low transition, so you put half of that. So you make it 1 and 1, and then you calculate the equivalent. So this is a high skew. High skew 2 input NAND gate. Okay, so then again we calculate GU and GD. GU, very simple, it is the same inverter, which is 2 and 1. Okay, GD, this time first we have to give the size for the NMOS transistor, which is same as 1 and 1. So 1 and 1 means this is R plus R equal to 2R. So this translates to W by L of 1 by 2. Okay, so this is 1 by 2, which means this is 1. And once we have the sizes, we can write GU equal to input capacitance of my gate, which is 2 plus 1, 3 divided by 2 plus 1, 3. 3 by 3 equal to 1. And GD equal to input capacitance of my gate divided by 1 plus 3 by 2. 1 plus 1 by 2 or 3 by 2 equal to. Again, we see the same thing. Okay, one transition, the NAND gate has improved. Okay, there is a question. Can you repeat the NAND gate part again? I'll do it again. We'll do a low skew version also of the NAND gate. Okay, so let us do a low skew option. Remove all this. Okay, so the circuit does not change. Up to now, we have been doing gates. The circuit does not change. Only the sizing is changing a little bit. So I'll draw the same NAND gate circuit again. Okay, so this time I want a low skew NAND gate. Okay, so I'll just recall what are the sizes of a normal NAND gate. 2, 2, 2, 2. Okay, this time I want a low skew 2 input NAND gate. Low skew means this pull down network part, right, is very critical for me. I cannot reduce the strength of these NMOS transistors. I will leave it as it is. So these are the same. Okay, but these two transistors, PMOS transistors, they are not important for my design. I can improve my performance by making them half of the original number. So half of that means you make it 2 by 2, 2 by 2. So the each of the transistors here will become size 1. So I'll erase this 2 by 2. Okay, so the NMOS transistors stay the same. PMOS transistors become 1 and 1. So this is the first step in calculating the transistor sizes based on the skew. Okay, so 1 second. Sorry. So this is the NAND gate. The first step is calculate the sizes of the transistors based on the low skew or the high skew. Okay. Then the GU and the GD. First step is get the equivalent inverter for that transition. That is the difference in these gates. Okay. So draw the inverter. So in this case, for the low to high transition, the inverter has to be the same as pull-up network, which is 1. And if this is 1, for a normal inverter, this will be 1/2, half of the PMOS size. And when we do this for the pull-down network, again, look at the pull-down network, 2 and 2. So this is nothing but R/2 plus R/2 equal to R. So this translates to W/L of 1. So put that here. This is 1, this is 2. That is the sizing we get for the normal transistor. So then you can write GD equal to input capacitance of my gate, which is 1 plus 2, 3, divided by input capacitance of equivalent inverter is 3. And here GU equal to input capacitance of my gate still says at 3, divided by 1 plus 1/2 is 3/2. This is equal to 2. So same as last case, it has changed. The critical transition, the logical effort has improved as compared to a normal. Remember that normal 2 input NAND gate G equal to 4/3. Okay. In this case, the critical transition logical effort has reduced compared to 4/3 also. It has come to 3/3. But the non-critical transition, it has increased from 4/3 to 6/3. And this is acceptable because we only decided that this GU transition is non-critical. So how can we improve the gate? So it could be that this gate is always in some gates, for example, the 1 to 0 transition might happen many times. Okay. But 0 to 1 transition may not happen so many times. So in those particular cases, we can use this skewed gate. 1 to 0, it will take very quickly. Okay, it will make the gate very fast, but 0 to 1 not happen so often. So whenever it happens, it will take little extra time. But because it's a rare event, we can ignore that particular occurrence. So this is the idea behind this skewed gates. Critical transition is the whole idea. Okay, and the sizing rule is whichever transition is critical, you don't change any sizes there, put the original sizes as before. The other set of transistors, okay, you make it half of the original size, and then based on the transitions, you calculate the equivalent inverter sizes and then the actual logical effort GU and G. So the next thing is this topic called as ratioed circuits, and there are many different this thing. Some theory is there, but for our particular syllabus, the family that we will see is this pseudo NMOS logic family. Okay, and pseudo NMOS even though we are going to study it, give the sizes, calculate logical effort, etc. It is not used in any of the practical situations, mainly because it suffers from one very important drawback called as static power consumption. And because of that, this whole logic family cannot be used, but it is of historical value because it evolved into dynamic circuits, dynamic logic circuit family. So we will just see briefly, okay, what is the, how to size these circuits. The block diagram is very simple, okay. It has one single PMOS transistor in the pull-up network, and this PMOS transistor is always on, okay. So it's an always on PMOS transistor. Why it is always on? Because it is permanently connected to ground. So we know that PMOS transistor, if it is connected to ground, it's going to have a on condition, and that's what's happening in this particular logic family. For permanently, okay, the PMOS transistor is on. You cannot turn it off, because you know in VLSI circuits, in ICs, you cannot change anything once the IC is fabricated, right? Once the connection is made, it is not possible to change it at all. So here also you cannot remove it. Sometimes you want to connect, sometimes you don't want to connect. That's not possible. It's a always on transistor. And how we can still work with that is by sizing the transistors appropriately. So that is the maximum work we do in this logic family, or in this particular design of this logic family. So two rules are there, okay. What are the two rules? One is the output, okay. So you can consider this PMOS as a resistor and this NMOS as a resistor. So even though we say that NMOS and PMOS are on, they are not perfect switches, right? They will have some amount of resistance. Only if you put a simple wire, you will have zero resistance. But if you have a transistor, and even though it is on, some value of resistance will be there, right? And how we can change that resistance? Suppose I have a transistor, okay. I have told this many times to my class. I'm sure the other teachers have also told this. As a digital designer, okay, you have control over only one parameter in the transistor. What is that parameter?
Width of the channel.
Width of the channel. And directly the width of the channel can control the resistance of the transistor. You think, like, suppose you have a very wide road, okay. Wide road means it is easy for many vehicles to travel. So in that case, we say that resistance is very low, okay. But if you have a very narrow road, then obviously there's going to be a lot of congestion, right? So in that case, the resistance is going to be high. Same logic for MOS transistors also. If the width of the transistor is very high, then current can flow easily from source to drain. Current flows always from source to drain, right? So source to drain or drain to source, that it can be either way, but the current flows from source terminal to drain terminal. And if the width is very high, then it has a lot of space for traveling, which means resistance is low. And if the width is low, obviously resistance is high. So in this case, in this particular family, what we are going to do is we're going to use that idea and try to design the circuits such that when both pull-up network and pull-down network are conducting, okay. Suppose only pull-up network is conducting, that is the PMOS is permanently on, that is true all the time. But suppose I'm giving some input, okay, you see one V input here, right? Suppose I give the input such that the NMOS network is not conducting. So very simple. In this case, suppose I give 0, okay, NMOS network is not conducting. Then output will be at perfect value, which is power supply. And that's what you see in the graph also. So what is this graph? Actually, this graph is your voltage transfer characteristics, okay, for the inverter. This is the inverter, right? Voltage transfer characteristics of the inverter only for different values of P, that is different values of PMOS transistor size. NMOS transistor size is fixed at 16, okay. And as the PMOS transistor size increases, you see for P equal to 4, P equal to 4 is actually not so bad, right? It's almost going down to ground, and output level is perfect value VDD. But for P equal to 24, this is not acceptable. That is when the output input is high, the output is at 0.3 volts, okay. So that is how we have to design these circuits. We have to design these circuits so that when the input is high, the output should be as close to ground as possible. And how can we do that? The idea is very simple. You make this PMOS transistor very small. That is the width of the transistor very small. Okay. So if the width of the transistor is very small, then the resistance across that transistor is going to be very high. So suppose you take 1.8 volts. Okay. Suppose this is 8R and this is 2R. Most of the 1.8 volts is going to fall across the 8R. Very small value is going to fall across the 2R. So that is how we can pull this V out as close to ground as possible. Of course, it's not going to be perfect. Okay, you see, even for P equal to 4, the output is maybe around 0.05 or something, but that is good enough. 0.05 is considered to be 0 only. But in this case, the sizing has to be done differently from before. Okay, the first rule is the PMOS network size has to be half in the original static CMOS gates that we did. Okay, the PMOS network size was double that of the NMOS network size. In this case, that is not true. The PMOS network size is half that of the NMOS network size. And unfortunately, that's not the end of the problem. We have one more condition also. The second problem, again, because the PMOS is permanently on, is that when the output is trying to go from 1 to 0, okay, that is, this particular node is being discharged, right? V out. Normal times when V out is being discharged, the PMOS network will not be conducting. But in this case, the PMOS network is always conducting. So even though, okay, so let's switch to the whiteboard. Okay, so in this case, what happens is when the PMOS network is conducting, when the NMOS network is conducting, so NMOS input is 1, so output is going to 0, but output when it is going to 0, this is all conducting, right? So this is trying to raise the output while this is trying to pull the output down. So the another condition is the effective current that is used to pull down, which is the difference. This current is to pull down, this current is pulling it up. Okay, so I NMOS minus I PMOS. This is the effective current that is discharging the output node. I effective, this has to be equal to VDD bar. Where this VDD, where did this R, all these things, where did they come from? Very simple. If you take a ordinary static CMOS, our good old static CMOS inverter, okay, suppose it is charging. In that case, this will be open circuit and this current will be approximately, okay, the difference in these two voltages, which is VDD, divided by the resistance of this transistor. This transistor size is 2. So 2R by 2 equal to VDD by R. The same way, when it is pulling down, that time this will not be conducting and the effective current pulling down the output node is VDD by R. So in this case also, we want that much speed, okay? And the second condition, the first condition is what we mentioned earlier, that is the size of the PMOS network should be half the size of the NMOS network. And the second condition also is required, that is the speed also should be as good as our static CMOS gates, which means that the effective current pulling down the node should be equal to VDD by R. So these two conditions we have to use together. If we use only one condition, we will not be able to get the sizes. Okay, so what is the meaning of that? We'll see with the example. Let's start with the inverter. So PMOS permanently connected to ground. and NMOS. Okay, so what I'm trying now to do is I want to put sizes for the NMOS and PMOS so that both the conditions we discussed are satisfied. Okay, and only when I use both the conditions I will be able to actually get the sizes. Right now I can use the first condition and say that if, let's call this as 2K. Okay, I don't know what is the size, but I'm going to put 2K, and normally I would put 4K for my ordinary inverters, right? But here I go completely in the opposite direction. I don't put 4K, I put K. Why K? Because half of the NMOS should be the size of the PMOS. This is how the two conditions. The first condition ensures that when the in my VTC, right? This is the ideal VTC of the static CMOS gates. We go perfectly to ground. This is region E. Okay, but in this case, it will never go perfectly to ground ever. But we want to try to make this as small as possible. And what is the condition we are going to use for that? This is the condition. The NMOS network should be double the size of the PMOS network so that this resistance, okay, is 2 times this resistance. So this is, in this case, if this is R, this will be 4R. Sorry, not 2 times, 4 times. Okay, and this is the condition that we are going to put so that the voltage transfer characteristics looks somewhat like this. The second condition is I effective equal to IN minus IP. Okay, IN MOS minus IP MOS. This should be equal to VDD by R. Now let us write this, okay, because we have to solve for this K. The first condition will just put this K. The second condition will allow us to actually solve for this, because this whole thing will be in terms of K. How can we write that? IN. Okay, so let's assume that the voltage across this is VDD divided by resistance of the NMOS transistor. Resistance of this is R by 2K. Okay, minus IPMOS. Let's assume that voltage across PMOS is also VDD. Resistance of this transistor. This transistor resistance is 2R by K. Not R by K, because per unit resistance of this is already 2R and the size is K. So 2R by K. And this should be equal to VDD by R. And now what we can do is we can cancel off all the VDDs, all the R's. So what we are left with is I wonder if this is correct. I don't think this is correct somehow.
Sir,
Yeah.
won't it be K by 2 in the equation you wrote now?
Which equation?
So the one on the left. 2K minus K by 2, no, sir?
Oh, is it K by 2? Oh, correct. VDD by 2 is there. So 2K minus K by 2 equal to 1. Yeah, this looks better now. Thanks. Yeah, 2K minus K by 2 equal to 1. So 2K minus K by 2 is K equal to 2 by 3. And this is the size that we put for the NMOS and PMOS. 2K for the NMOS, which means this will be 4 by 3. 2K is 4 by 3, and this is K is 2 by 3. And this will give us both speed and good value for VOL. Okay, so this is the sizing way for pseudo NMOS gate. So let us try one more example. Let us try a 2-input NOR gate or something. So we didn't do one thing, we didn't calculate the logical efforts. We'll do that for this gate. So let us take a 2-input NOR gate. Okay, so again, I don't know what sizes I have to put. So I'll just put some K and K. Okay, and what should I put for the PMOS transistor? Can you tell me? I have put K and K in terms of K only. You cannot get the direct answer, but in terms of the variable K, what size should I put for the PMOS transistor according to the first sizing rule?
K by 2.
K by 2. Okay, I don't know what it is, but according to the rule, it should be K by 2. Then second rule, write the current and then try to solve for K. So in this case also, assume only one transistor is conducting, worst case. So I effective equal to VDD by R by K by 2. Oh, sorry, R by K minus two R by K by 2. And then this should be equal to VDD by R. And then solve for K. So K, cancel all the VDD and Rs.
So,
Yeah.
so why is there only one PMOS transistor?
That is the rule for pseudo NMOS gates. Whatever is the gate, there is only one PMOS transistor which is permanently connected to ground. That is the block diagram. Like we have the block diagram for static CMOS circuits. For pseudo NMOS gates, the block diagram is like this. Okay, one PMOS transistor permanently connected to ground, and then whatever comes in the pull down network, the inputs are only given to the NMOS transistor and ground. This is the block diagram for pseudo NMOS. So whatever function you want, you implement them using only the NMOS gates. This is the design of the pseudo NMOS gates.
Okay.
Excuse me, sir.
Yeah.
Can you explain how did you write the expression for I effective once again?
So I effective is equal to I NMOS, which is discharging the node, minus I PMOS. What is the meaning of I effective? I effective is nothing but effective current discharging the output node. Okay, so we said that output node is going from 1 to 0, that is like this. But when this is happening, this is also charging the output node. So the effective current discharging the output node is the difference between NMOS and PMOS. This is the first thing to remember. Okay, then each of the currents you write separately. You look at the NMOS transistor network. In this case, there are two transistors in parallel, and whenever there's parallel, we take the worst case for the sizing. Worst case is when only one of these is conducting. Okay, and in that case, the single transistor is going to have a resistance R divided by K, because the NMOS transistor unit resistance is R, and divided by the W by L of the transistor. This is the resistance, and we assume that the voltage across the transistor is VDD. That is, this much is VDD. So this I NMOS that I have written, okay, it is just the approximate value. It's not the exact value. It's just some sort of an average value using Ohm's law. So VDD by R by K. And for the PMOS transistor, again, we assume that voltage across the transistor is VDD, okay, divided by resistance of the PMOS transistor. That is 2R unit resistance divided by the W bar. And this should be equal to VDD by R, because this is the effective current in static CMOS circuit. So this equation, the first equation, that is the first sizing rule, ensures that the VOL goes as low to ground as possible. This rule ensures that the speed of the gate is also good. So both are required for the proper operation. And this second equation will let us solve for the actual K. So in this case, I'll try to solve. Let's say we cancel off all the VDD and R. So RHS is going to be 1. This is going to be K minus K by 4. Okay, and this is K equal to 4 by 3. So then you just put the same thing here, same as the previous case. So just clear this whole screen. So 4 by 3 and 4 by 3. Now logical effort. Okay. Now logical effort. Thankfully, we have done this skewed gates. So logical effort in this case also, because these two networks are not equivalent, we have to calculate the GU and the GD. So two by 3, and here this is 1 by 3. Okay, half of the NMOS, and GU now be careful, input capacitance of my gate. Okay, in this particular gate the input is only given to the NMOS transistor. Don't add NMOS and PMOS. PMOS is permanently connected to ground. It doesn't come into the picture at all. GU is just 4 divided by 3 divided by 2 by 3 plus 1 is 3 by 3 or just 1. So this is equal to 4 by 3. Okay. Now GD, and this is the lucky thing for all the pseudo NMOS gates, GD is just always, your sizing is equivalent. You don't have to do anything. It is always equivalent to 2 and 1. Okay, don't even think. So always for all the gates, the GD equivalent inverter is 2 and 1. Okay, so your GD is just going to be 4 by 3 by 2 plus 1 is 3, which is equal to 4 by 9. Don't calculate the equivalent inverter. The reason why we can do this is when we did that effective current, this thing, right? We equated the effective current to VDD by R. And this means that your equivalent inverter is 2 and 1. And since we do this for every gate, in every gate, the equivalent inverter is only 2 and 1. So whatever it is here, just divide that by 3, and that is the GD value. And this is the logical effort for the rising and the falling transitions. And this basically is your pseudo NMOS logic family. Okay, it's a completely different logic family compared to static CMOS. The logical effort is better, like you see here, but the problem why this is not used anywhere, the size is also better, right? Because if you take any equivalent gate in static CMOS, it will have more transistors. In this case, the number of transistors is reduced because only one PMOS is there. The only difference or the only problem why this cannot be used in practical situations is that it has this unavoidable problem called as static power consumption. So the next logic family that we will see also.
Sir,
Yeah.
Sir, could you repeat the part for PMOS again, sir? The logic calculation for the GU part.
GU part. So just like in the skewed gates, you look at the rising transition. Okay. What is the size of the network for the rising transition? It is 2 by 3. So you put that directly 2 by 3. Okay. And if you look at the equivalent inverter for any static CMOS inverter, the NMOS size should be half of the PMOS size. So 2 by 3 is the size of PMOS, means NMOS should be half of that, which is 1 by 3. So this is your rising transition. This is the equivalent inverter for the rising transition. Once you have that, you can do the GU calculation. GU equal to input capacitance of my gate. Again, even though we are looking at the rising transition, the input capacitance is only 4 by 3. Okay, it's connected to the NMOS transistor, divided by input capacitance of equivalent inverter. Input capacity equivalent inverter in this case is 2 by 3 plus 1 by 3 or just 1. So 4 by 3 by 1 equal to 4 by 3. Okay.
Yes, sir.
So you can try this in the book. There's some more this thing for other 2 input and 3 input gates. So you can look at that from the book itself. Okay. So let us move on to the next and last logic family, which is the dynamic circuits. Okay, so let us start with the block diagram. It is somewhat similar to the pseudo NMOS, only that the PMOS is given this new signal phi, which is your usually like a clock signal. Okay, and this circuit, okay, this first circuit allows us to avoid the problem of static power consumption, and the concept is very simple. Clock signal, the same clock signal is given to both the NMOS and the PMOS transistors. Okay, and when that signal is low, that is when phi equal to 0, then irrespective of what the input values are, y is going to be at logic high because of the PMOS transistor connected to VDD on the other side. So the operation in this case, we go to the operation itself. The operation is a little bit more complex. Okay, it is divided into 2 stages based on the clock signal. So when the phi equal to 0, you see in this diagram, the output is definitely going to be at high only. Okay, it cannot be at any other value because the PMOS transistor is on. It is connecting the output to VDD. And the other thing is, when the phi equal to 0 from this diagram, okay, we see that this bottom NMOS is going to be off. So definitely the output cannot be connected to ground. So that is the problem we were having in the previous pseudo NMOS family. The output node is connected to both VDD and ground through the NMOS and PMOS, which are simultaneously conducting. In this case, because of the clock network and this transistor we have put below, the output cannot be connected to both VDD and ground. So we don't have to worry about that problem at all. Okay. So the first phase, when the clock or phi equal to 0, irrespective of the input values, the output is definitely going to be at 1. And that is what is shown here. Okay. When the clock becomes 1, then the PMOS stops conducting. PMOS transistor is on top. So when phi equal to 1, PMOS is off, but now the NMOS is on. Okay, and in the previous stage, Y was pre-charged to high. In the evaluate stage, what is shown here, Y, it can continue at 1, or if the inputs are such that pull down network is conducting, then Y will fall to 0. And this is the evaluate stage or evaluate phase, where the inputs are being evaluated. That is, the input values are being observed and the output is calculated based on the input values. So this is the modification to the pseudo NMOS family, where instead of having a PMOS permanently connected to ground, we just change it slightly so that a clock signal connected to the PMOS and NMOS avoids that particular condition. So all the sizing, etc., all that is gone. We don't have to worry about anything. Okay, sizing in this case becomes very simple. By default, you see all the gates here, the PMOS size is constant, which is 1. Okay, the NMOS, just like we were doing for the static gates, the same thing. Okay, you might have 3 transistors, 4 transistors, series, parallel, etc. The NMOS network together should equal a single transistor of W by L equal to 1. You put the sizes accordingly, and that is what you see in all these examples. First, we will look at the inverter without the footer transistor, one single inverter, one single NMOS transistor, so size is 1. Then you go to the footed version, that is the footer transistor is also there. So together both of them have to equal one single NMOS transistor whose size is 1. So you put 2 and 2. Okay, and the same thing for NAND, NOR, etc. Much simpler compared to the pseudo NMOS sizing. Very simple, just like you do for static CMOS circuits. If the unfooted version, just the transistors for the network is there. In the footed version, one extra transistor with the clock signal will come into the picture. And when you're doing the transistor size calculation, you have to include that transistor also. Okay, so instead of, even though in this 2-input NAND gate, you see the middle picture, bottom footed row, even though it is only a 2-input NAND gate, there are 3 transistors in the pull down network, because third one is the footer transistor. And when we are sizing these transistors, we also have to treat this footer transistor as a normal transistor. So all 3 together have to give me resistance equal to R. So just like you do for a 3-input NAND gate, you put 3, 3, 3, right? Here also you do the same thing, put 3, 3, 3. Okay. Logical effort calculation also very simple. In all of these cases, equivalent inverter is 2 and 1, and you just have to see what is the input capacitance. In this case, it is 2, 2 by 3. In this case, it is 3, 3 by 3. In this case, it is 2, so 2 by 3. So much more simpler this thing, but only this thing is the operation is little bit more complex. We cannot just give the input and expect the output. We have to give the input. We have to pre-charge the output node, and in the evaluate phase only we should observe the outputs. So this is the design of dynamic circuits. Very simple, easy to understand, but there are some complications in the dynamic circuit, this thing. So we'll see one example here. Okay, so let's say this is our input and this is my output signal. Okay, and in the pre-charge phase up to this particular point, so I'll save this, switch to the whiteboard. Okay, so up to this particular point, no problem. Okay, whatever the value of the input, the gate is in the pre-charge phase, so output is at perfect value 1. Then the evaluate phase starts. Okay, in the evaluate phase, in the beginning of the evaluate phase, okay, A is equal to 1. So basically this is static CMOS, sorry, it's a dynamic CMOS inverter. So let me draw the circuit. 1 second. Okay, so this is the circuit, and they're showing the output when when phi equal to 0, no problem, output is at 1. When phi equals to 1, okay, now the evaluate starts, and if you see this particular input combination, A is equal to 1, right? So as soon as the evaluate phase starts, A is equal to 1, so this transistor is going to be conducting, and phi is also equal to 1, which means this is also going to be conducting. Output is discharged, and that is what you see at the beginning of the evaluate phase. Then what happens in between? Suddenly A makes a transition from 1 to 0. So this is an inverter and A goes from 1 to 0. Output has to go from 0 to 1, right? This is what the inverter is. But you see here, output continues to stay at, let's go to red color. Output continues to stay at 0. Output cannot write. The dotted line that you see is the correct value of the output. But that can never happen. The reason for that is phi equal to 0, which means that this whole top part is disconnected. The output node is floating. Okay. And this is the problem with dynamic circuits. The 1 to 0 transition is not allowed. Okay, because it can cause this type of errors. 0 to 1 transition, do you think that will happen? Let us see if we can draw the waveforms for 0 to 1 transition. Okay, and see if we are getting an error or not. So let's draw a sample waveform. This is my clock phi. This is my signal A. So up to this particular point, when clock equal to 0, A is basically don't care. I don't care what the value of A is. Okay. At this point, let's say that it makes a 0 to 1 transition, and I want to see if the output is correct. So up to this particular point, output is going to be high. Okay. And at this point, the input A is 0. So I'll draw the circuit again. One PMOS transistor, one NMOS transistor that is given the signal A, and one more NMOS transistor which is getting this clock signal phi. Okay, and this is the output node. So when A is equal to 0, this transistor is not conducting. So output, this transistor is also not conducting. So output can not discharge. Okay, it will continue to stay at 1, stays at 1, and that is what we will see first. And once A goes from 1 to 0, from 0 to 1, then output will fall. Then suddenly this will start conducting and it will get discharged. Okay, and this will stay discharged till the next pre-charge phase. So this is okay. So 0 to 1, okay transition. 1 to 0, not okay transition, because we saw in the previous example, 1 to 0 transition, the output is not correct. So basically that is one problem with dynamic circuits. The 1 to 0 transition is not allowed for the input during the evaluate phase. So how can we solve this? Because it's a very restricted transition, right? You're saying there can only be 2 transitions. Actually, there can be more. It can be 1 to 1, 1 to 0, 0 to 1, or 0 to 0. But the one of those, if you're not allowing, that's a problem. So how can we solve that? Very simple. We can solve that with a small modification. So let's go back to this, please. Okay, so we can modify that with a very small addition to the output node, and this particular logic family is called as the Domino Logic family. Once again. So the Domino Logic family, the structure is about 80–90% also you can say is the same. Okay, only addition is at the output node you add a static CMOS inverter. That's what you see in the block diagram there. There's a 2-input Nand gate. Okay, and instead of just taking W as the output, which is what we were taking before, we take W and we pass it through a static CMOS inverter, and that forms the output X. Okay, And in this particular case, as you see in this waveform, the 1 to 0 transition is completely eliminated at the output X. Okay, so the reason for that is in the pre-charge phase, okay, W can be in the pre-charge phase, W will definitely be at 1. And if W is at 1, X is going to be at 0. Okay. So in the evaluate phase, W can go from 1 to 0, or it can stay at 1. If W stays at 1, X will stay at 0. If W goes to 0, then X will go to 1. So basically, if you ignore W, which is somewhere inside the gate, we are only seeing the output X. We see that only transitions possible at X are 0 stays at 0 or 0 to 0, or 0 goes to 1, 0 to 1 transition. And that can be given to the next stage, because X can never have a 1 to 0 transition based on the analysis that we have done. So this is the minor modification to dynamic logic circuits to remove the constraint on the output transition. In this case, output will never have a wrong transition, and we can pass that output reliably to the other gates. And this particular logic family is called as domino logic. And the only disadvantage, just like static CMOS has the disadvantage that it produces inverted outputs, the domino logic has the disadvantage that it cannot produce inverted output, because naturally we are adding a inverter to the output, only the non-inverted output. So you see this example, right? It's a domino AND gate. You cannot get a NAND gate directly. So this is the end of the logic family. The next two topics are not that important, so we will skip them. Okay, so let's go to the last topic in Unit 5, which is basically very, very important from a practical perspective, because it includes a lot of the basic concepts for this physical design, which is a very important domain in VLSI industry in India and around the world also. So physical design, your teachers also might have talked to you. It's all about designing the circuit so that all the timing constraints are satisfied. There are other constraints, power, area, etc., but those are very difficult to reduce from a layout perspective. Okay, from a layout perspective, the only thing that you can do as an engineer, physical design engineer, is to add buffers or try to modify the floor plan, etc., in order to improve the timing constraints. So what are the timing constraints? What is the meaning of this setup time, hold time, etc.? All those things we will see in this particular topic. Okay, so the first thing is, in most modern designs, the blocks, the combinational blocks and the sequential blocks, they're basically used together, just like it is shown in this diagram here. Okay, that is, there will be some combinational logic. This might be something like a graphics engine or a neural network engine, or something even smaller, much smaller than that also. And before and after, okay, that is, the inputs of the block, they will not come directly from another block. Okay, the inputs of the inputs of some other outputs of some other block will be given to a register, and this particular combinational logic will get the inputs from the register or latch, and the outputs also are given to another latch. So basically, this is what is called as the sequencing elements. Okay, in this case, the combinational block is there, and before and after the combinational block, we have these sequencing elements. What is the meaning of sequencing? It's just elements that are there so that the inputs are properly given. Okay, that is, the inputs are given properly and the outputs are taken at the correct time. Okay, so we said one example when we were doing this input ordering, this thing, right? The different inputs are there and they might arrive at different times. Okay, but we should not sample the inputs until the until all the inputs are ready. We should not sample them. That is what is this first flip-flop is doing. that only. Okay, some other block is producing it, and we should not take the partial outputs. We should take the correct outputs. And the output side flip-flop, that also is doing something similar, but for our particular combinational block. We should not give out the partial outputs only when all the outputs, like you might have 4 outputs, some combination block might produce 5 outputs, etc. Right? How many of them? Only when all the outputs are ready, it should be passed on to the next block. So that is what these two flip-flops are doing. They're basically controlling the sequence of the inputs and outputs being produced so that the correct inputs are sampled and the correct outputs are sent to the next block. And all this is done with the control of the clock signal. The clock signal is one of the most, I would say, single most important signal in all integrated circuits, because all the complete operation, two things. One is the complete operation of the clock of the IC depends on the clock signals. Okay, and number two is the clock signal has to be given to all parts of the IC. Okay, the clock signal is so important. It has to be distributed through the IC, because through the IC, this type of sequencing elements will be there, and they have to be given the clock signal for the proper operation. Okay. Let us look at some definitions. Again, not too much calculation or anything, just some simple definitions. So we have two different elements here. You might have seen this in previous units. We have one element called as the latch, and the other element is called as a flip-flop, and they're just showing some sample waveforms for the latch and the flip-flop. And we already know this. The difference between latch and flip-flop is that latch is level sensitive. That is, whenever the clock is high, the output of the latch can change. So same signal D is given to both latch and flip-flop. But if you see in the latch part, when the D goes high and the D comes back low, the Q of the latch follows that D. Okay, but in the flip-flop, that cannot happen. At the beginning of the clock cycle, at the clock edge, the D was 0. So output is 0. So in between, even if D changes, output will not change. Only in the next clock edge, the D will be sampled. At that time, D is high, and that D comes to the output of the flip-flop. So this is the only difference. Both latch and flip-flop can be used for sequencing, but we have to remember that latch is level sensitive and flip-flop is only edge sensitive. So some simple definitions based on these operations. So propagation delay we have seen many times. It is a logic propagation delay. What is this logic contamination delay? Contamination delay basically is there is some amount of inertia. Okay, so suppose some logic block, take a simple block like Nand Gate. Okay, so in our inverter voltage transfer characteristic, so let's switch to the whiteboard. So let's say that I wanted to calculate the contamination delay of a inverter. Propagation delay, we know how to calculate, right? You put the 50% TPHL plus TPLH by 2, that is your propagation delay. But what is this contamination delay? Okay, so let's say that this is my input. So the output will be low, and let's say that this is where the input starts changing. Okay, and let's say that this is some value, and I'll say what this value is. I'll use a different color for the. Okay, so if you remember in our VTC, there was one region A. Okay, that region A in the VTC, okay, input has increased. So maybe I'll draw this upside down. Erase this. Let's say that this is the input, and It's green. Okay, so this is your identical. This is nothing but your VTC curve. Okay, input versus output. Input is increasing, output is falling. And this part is your region A. Okay, because in region A, the output stays at high, even though the input has gone, and this is VTN. The NMOS transistor is still not conducting. Okay, up to that particular point, the output stays at the constant value. This amount of time is called as your T contamination delay. Okay, this amount of time, basically the output does not change. The output has not responded to the input. It continues to stay at the previous value. It could be high or it could be low. It doesn't mean that only for high value. This will happen for low value also. But for some amount of time after the change of the input, this you can consider as inertia. Okay, you know what is inertia in the physical world, right? Like there is some amount of resistance for the action to happen. So in some case, you can think of this also as the same thing. There will be some amount of time before the output starts to respond to the input. Okay, that small amount of time, TCD is a very small amount of time. Okay, it's not big like propagation delay. You will not get you'll not get 50 picoseconds. Much smaller, 2-3 picoseconds. But it is still not zero. There is some amount of time before it starts to respond, and that is called as the contamination delay. Okay, so this you might not have heard before, but it's a very simple concept, very similar to our inertia. So this is one delay, propagation delay. Then there is the contamination delay, and then the latch or flip-flop clock to Q. That is the delay from the clock edge to the output. Some value is there at the input, okay, and the clock edge has come, and that should go to the output, and that is called as the propagation delay from clock to Q. The suffixes tell us the whole thing. TP, whenever it says TP, it is propagation delay. From where to where? Between the clock and the output Q. That is TPCQ. TCCQ is the same thing. Okay, the clock has come, but the output has not changed. How much time is there like that? Okay, definitely output has changed. When the clock comes, output has to change. But like we saw in the previous example, there will be some amount of time for which it is not changing. It continues to stay at the previous value. That particular amount of time is called as the contamination delay for clock to Q. And then TP DQ. TP is propagation delay. D to Q is from the D input to the Q output propagation delay. Similarly, TC is the contamination delay from D to Q. T setup and T hold. These are very, very, very important times, important timing requirements. Setup time and hold time. Setup time is, I'll use this thing, whiteboard. Okay, so let's say that we have a clock signal and we have some other value D. Okay, before the arrival. We don't care what the actual value is, it could be anything, but the clock edge has arrived. Okay, and from the middle, from the 50%, if I put a vertical marker, there should be some amount of time before that where the input D is not allowed to change. We cannot change it. Okay, and this is a number that is particular to some particular IC, some particular design, etc. And that number, okay, it could be something like 8 picoseconds. This could be something like 6 picoseconds. This will be very, very important, and we cannot violate this timing constraint. This is called as a timing constraint. There are many timing constraints. Setup time is one constraint, hold time is another constraint. Setup time constraint says that some amount of time before the arrival of the clock signal, okay, you are not allowed to change the input. You should have made sure that at this particular time point, okay, your D is at the final value, and that is what this clock is going to see, and that particular amount of time is called as the setup time. On the other side, okay, after the arrival of the clock signal, there is some amount of time for which again you should maintain the D at the same value. You're not allowed to change the D during that time. That particular amount of time, what is that duration for which it should be held constant after the arrival of the clock signal? That particular timing number or timing constraint is called as the hold time constraint. Okay, why you set up time, hold time? Very simple, but very, very important. Its importance cannot be this thing. Suppose I have a clock signal, okay, and we know that in designs nothing is perfect, right? Now theoretically the clock signal this could be at something like, say, 400 picoseconds. The clock arrives. This is the theoretical according to the designer who's working with the simulation tool. But in the practical setting, because of the delays, etc., it might happen that the clock actually comes at 360 picoseconds. Okay, and this is the reason why this setup time constraint is there. This could happen. Okay, this could happen in many cases. The clock can come before or after its actual this thing, and this deviation is called as the clock skew, like just like we saw in the skewed gate, right? Skewed gate means we are skewing the delay towards one side. In this case, the clock signal itself is skewed. Okay, and this could happen in many these things. It happens all the time. But even with the skew, if I want my circuit to work, then I need this setup time constraint, because even with this much amount of skew, right, we see that D is already at its final value. Even if this clock skew happens, the correct D will be sampled by the input at this particular clock cycle, and that is why this setup time constraint is present in all digital designs. Okay, because of this phenomenon called as clock skew, the clock can be pushed forwards or backwards. Even with this, we want the correct input to be sampled. To allow that to happen, you have a constraint. At some amount of time before the arrival itself, D should have settled to the correct value. That amount of time is called as the setup. After the clock signal has arrived, why is there a constraint? For that, you can look at the design of the latch. If you remember, it's nothing but two back-to-back inverters, right? So when these back-to-back, I'm not drawing the transmission gate, but there's a transmission gate also. After the arrival of the clock signal, this is D, this is Q bar, and then there'll be one more here, which becomes Q, etc. But you have to leave some amount of time for this to propagate and then settle down at this value, and for that value to start circulating here. Okay. If before that itself you change this D, then you could have put a 1 before and 1 is trying to get stored here, but then you're taking 1 to 0 and then this goes somewhere and the clock goes away and some intermediate value starts circulating and it might destroy the whole thing. So that is the reason for this hold time constraint. You should allow some time for this particular feedback loop to settle down before you can change the input, and that particular value is called as the hold time. So these two constraints are very, very common in all digital design. And literally the biggest task of the physical design engineer is for satisfying these setup time and hold time constraints. They will have something, the tool will run and the tool will create setup time and hold time. Tool will not create, but even after the tool produces the results, there will be some setup time and hold time violations, and the physical design engineer has to do something at the layout level to remove those particular violations. Okay, and these are all the definitions that we're going to use to see what is the clock period we can have for our design. So, okay, so this is the diagram, combinational logic block input. Okay, you see the input has come, that is the input has changed at this particular point. Maybe I'll save this to the whiteboard. Okay, so let us start with the first one. This is the very simple one. So the input has come at this particular point. Okay, so how do I make this straight? So maybe I can't make it straight. So I'll just draw. So the input has changed at this particular point. Okay, and up to this point, the output does not change. And this difference between these two, where the output is still maintained at the previous value, this is called as the contamination delay. And after some time, the output says, oh, okay, input has changed, I should start changing. Let me do something. Then it goes through some transitions up and down, up and down, up and down, etc., until it settles down at the final value. And this, from the arrival of the input up to the settling down of the output at the final value, that 50%. We have done this many times in the lab, right? TPHL, 50% marker, same thing. And the initial value up to where the previous output is being maintained, that is the contamination delay. When the final output is available, 50% of the input to the 50% of the output, that difference is your propagation delay. So basically the difference between these two is your, this length of this line is your contamination delay. Length of this line from this point to this point is the propagation delay. So this is the simple, this thing, only thing is we've added this propagation delay, no, sorry, contamination delay. Okay, so next let us go to the flip-flop. So flip-flop, little bit more complicated because there are three signals. There is a clock signal, there is the input D, and there is the output Q. So whatever we mentioned in the previous slide, we're just going to see those in terms of these particular diagrams. So this first one, that is the input is at some value, we don't know what it is, then it settles down to the final value. This settling down, okay, should happen at least T setup amount of time before the clock edge. You're not allowed to change the input after this particular point. That is called as the setup time constraint. So that difference between the clock 50% to the final value of D settling down is your setup time. After the arrival of the clock signal, then D is sampled. Output Q doesn't change for some time. Okay, and that amount of time from the 50% clock to the 50% output changing for the first time is called as the clock to Q contamination delay. TC is for contamination delay. It's from the clock signal to the Q signal. And similarly, the output will eventually settle down to its final value. That is T propagation delay clock signal to Q signal. And immediately after that, we are not allowed to change the value of the input also after the arrival of the clock signal, for some amount of time, the input D should be held at the same value. That particular constraint is your hold time constraint. So overall, all the constraints we saw in the previous slide, they have defined in this diagram. Setup time before the arrival of the clock, it should be constant. Clock to queue contamination delay, clock to queue propagation delay, finally hold time constraint. And same things for the latch also. After some time, the contamination delay, propagation delay, and then setup time, hold time. Same things for the latch also. Only thing is, because the latch has level sensitive, it can change in between, and we see those changes also here. Okay, that is in between when the D changes, D to Q contamination delay, D to Q propagation delay, because the latch is level sensitive. As long as the clock is high, those things can change. Okay, and these are all the definitions in terms of timing. So based on these definitions, what we are going to see is these all definitions, these all timing constraints, they have to be satisfied. Okay, so if we have to satisfy all these timing constraints for some particular combinational logic block, what is the smallest clock period I can use for my design? That is the whole thing that we want. Okay, these timing constraints we cannot violate, they have to be satisfied. So with all these timing constraints, what is the smallest amount of clock that is going to be possible such that all the timing constraints are going to be satisfied? So that is the next calculation that we're going to see, just a simple summation based on the waveforms. Okay, so the first constraint is called as max delay constraint. Okay, so again, this is the familiar diagram that we have been talking all about. There is a sequencing element added before the combinational block. There is a sequencing element added after the combinational block, and there is the same clock signal Q. So first we see the clock signal, the total clock period TC. Okay, this is the one that we want to decide. We want to decide such that the TC, okay, we want to keep it as small as possible, because generally in all your advertisements, etc., right, high number for the frequency or high number for the clock frequency is considered to be a good thing. It's not always a good thing, because it comes with other issues like power, and not necessarily that simply increasing the clock will increase the throughput also. But generally, for the sake of marketing, etc., we want to keep the clock as small as possible. So based on all these constraints, we want to set that TC, and that is what we see in this diagram. The clock edge has come, okay, and after the clock edge has come, the output Q1. So we are concerned with D2, okay. Q1 is one signal, which is the output of the flip-flop. Then the output of the flip-flop goes to the combinational block. It forms the input to the combinational block, and the combination block in turn produces the output D2. So these are all the things that are happening here. So first the clock, it goes, then there's the propagation delay from clock to the Q. So then after that much time Q1 is available, then the combinational block has to calculate its output, the propagation delay from the Q to the combinational block, and then the output of the combinational block should be such that it should be available before the next clock cycle. So that is the setup time. So your total time for the clock TC should be greater than TP, clock to Q. That is, the output is produced, Q1 is produced, then the propagation delay of the logical block plus the final setup time constraint for the design, because the next clock cycle has come, and for some amount of time before the next clock cycle, output D2 should be settled at the final value. So together the TC should be greater than or equal to TPCQ plus TPD plus T setup. This is called as the maximum delay constraint. This is the constraint. If you rearrange this, okay, this TPD, just rearrange this equation, put TPD on one side and take setup and PCQ to the other side. So the maximum possible delay for your combinational block. Okay, suppose you are working in some particular design, but already, because this clock signal is a very, very crucial signal, I've already sent that, right? So the period and this pulse width, all these things, every person cannot change. You cannot say, hey, give me this clock signal with the period 10 and pulse width 4. You cannot do that, okay? Because for a large design, the clock signal is the same, which means the period and the pulse width are the same. So we cannot change that TC. Okay, what we have to do, we have to work such that our combinational block satisfies this last equation, TPD. The maximum delay possible for your combinational logic block should be at most TC minus setup time plus TP-CQ. This is called as the sequencing overhead, but this is the maximum delay for your combinational logic block. Any delay more than this, then it is going to create a timing violation and you have to redo the design. So this particular design, this particular equation which gives us what is the maximum delay for our combinational logic block, TPD, maximum propagation delay. This is called as the max delay constraint. Okay. So similarly, we can have a min delay constraint. In this case, we have a slightly different diagram. We have a same thing actually, clock Q. Okay. The min delay is another thing which comes because of this particular diagram. The clock edges come, okay, and after some time the Q1, okay, contamination delay happens, and after that Q1 begins to change, and Q1 begins to change, and that change in Q1, okay, is going to affect the output of the combinational block, because Q1 has begun to change, and after some amount of time, that is the contamination, propagation delay of, wait one second, both are contamination delays in this case. Contamination happens at Q1, because of which the input to the combinational block starts to change and the output also starts to change after TCD, okay, and then D2 is going to start to change, and the sum, that is because of the hold time constraint, for some amount of time D2 should be at a constant value after the arrival of the clock edge. So this basically says that the contamination of Q plus contamination of D should be greater than the hold time, and they have rearranged it so that the TCD, that is the contamination delay, is only on one side, and they have rearranged it to give you this equation. This is called as the min delay constraint, the contamination delay of your logic block. In both the cases, the constraint is related to your combinational logic only, okay, because that is the only one that we can change. The flip-flop and all is not in our concept. Flip-flop will be a standard cell. Everybody is using the same flip-flop. I cannot change the numbers for the flip-flop. The same thing for the clock also. The same clock is used for the whole design. I cannot change anything there. The only thing I can change is the propagation delay of my block and the contamination delay of my block. So the first constraint is the max delay constraint, which says what is the maximum possible propagation delay that your block can have. The second tells what is the minimum possible contamination delay. Your contamination delay should be greater than that number. If it is not greater than that number, then you will have a hold time violation. So these two are the max delay and min delay constraints. So the last concept is called as time borrowing, and it's sort of a complex thing. I'll let you read it on your own. I don't think we have too many topics related to this. So time borrowing is not that important. I'll maybe give you some notes later on because it's difficult to explain. Again, these two topics we have already mentioned many times. The combinational block, okay, the clock signal, the edge of the clock signal, you see that there are many edges, right? And this is the meaning of the clock skew. The period of the clock, TC, okay, that is fixed. That rarely changes. It changes sometimes, but that's a different phenomenon called as jitter. In most cases, the clock period will stay the same, okay, but the edge, the arrival of the edge can be pushed forward or backward. This is because of the delays in the wires, because the wires, the delay is there. Some wires, the neighboring wires may be switching, and the switching will be different. So in different parts of the clock network, the the clock skew will be slightly different. That's what's shown in the diagram also. But the maximum number is given as T skew. What is the maximum amount of which the clock can change? And in that particular case also, your design has to work. And they've given you one more constraint with respect to clock skew. This is basically, the first one is your max delay constraint. The second one is your min delay constraint. But in this case, they're also accounting for the variations due to clock skew. So it is very similar to max delay and min delay. Only thing is the clock skew number has come into the picture. So if you see the propagation delay problem, okay, the propagation delay, the maximum amount of propagation delay has reduced because the next clock cycle might come earlier, which means that the amount of time required for the logic block is even smaller. So your propagation delay has suffered because of the clock skew. Originally, if say your maximum propagation delay for your block was 50 nanoseconds, if the clock skew is 5 nanoseconds, that means that in 45 nanoseconds itself, your output should be ready. You don't have the full 50 nanoseconds. The same thing for the contamination delay. Okay, the contamination delay should be greater than, in the previous case, it was just T hold minus TCQ. This was the max, this was the minimum value for the contamination delay. Anything greater than this is okay. In this particular case, the minimum value has increased. Okay, that is T hold minus TCQ plus T skew. The minimum value of the contamination delay has increased because of the clock skew. And this basically is just a modification to include the effect of the clock skew. Okay, latches and clock skew is also not that important. So we have covered everything except this topic on time borrowing. Time borrowing separately, we will write some this thing and I'll pass it around to all the classes. Okay. So that is all the topics in Unit 5. Unit 5, there are 0 numericals. Okay. It's just a lot of design-based problems for 75% of the topics. Dynamic CMOS, domino, ratioed circuits, bubble pushing, input ordering, etc., compound gates, skewed gates. And then 25% is all these definitions related to timing, sequencing elements, min delay constraint, max delay constraint, clock skew, time borrowing, etc. So there are no numericals at all. The second part, directly whatever definitions you have seen, only that will be asked. The first part will be some gate level, this thing, dynamic circuit, ask what is the dynamic, what is the drawback in dynamic circuits, why do we need domino circuits, something like that. Okay. So this is the end of Unit 5. These slides have been shared to A section. You can get it from your classmates. So I'll stop here. If there are any questions, you can ask related to this Unit 5.
Sir,
Yes.
are you saying topics like time borrowing will mostly is less likely to be asked in exams?
No, time borrowing is equally likely to be asked. That SOI and other thing, sub-threshold circuit design, even though it's there, we don't cover it much. But time borrowing can be asked.
Design of it.
Design of what?
A time borrowing, the whole thing, the derivation of equation, all those.
Yeah. Those can be asked. But whatever is in the slide, only that. Okay. They cannot ask you anything new because these are all standard definitions. You cannot come up with a new definition in 3 hours examination. So min delay constraint, max delay constraints, with skew, without skew, etc. Whatever is the slide is just a direct reproduction, like the adder unit, right? Carry save adder means it's fixed. Whatever is there in the book, exact that you have to reproduce. Here also the same thing. For all the timing related concepts, whatever is there in the book and the slides, which is the same, you just have to directly reproduce. But all of them that are there in the slides can be asked. If you see the previous 1 or 2 years question paper, time borrowing has been asked, I think, at least once, if I remember. But there is no design as such. You cannot design a circuit. You cannot create a circuit as well. You can only explain what is the min delay constraint and what is the derivation of the actual constraint from the waveform.
Okay, sir.
but they can ask you a question in terms of the numbers. Okay, in the textbook also there is one question like that. If you see it, you will understand. Instead of asking you to derive, they have given you the sample, a sample clock period. Okay, and then a sample value for TC, T-skew, etc. And they're asking you to calculate what is the possible maximum possible propagation delay for the logical block. So you just have to use that equation with those numbers.
Okay.
Okay, any other questions? Okay, so thank you. We'll end this meeting.
Thank you, sir.